Cast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the webinar. We will be starting in just a few moments from now. Thank you. Hello, everyone, and welcome to our webinar. And in continuation with our series of webinars on what's new in SolidCAM 2019, today's webinar will be on simultaneous 5-axis. Now, we've done a lot in the past years in simultaneous 5-axis, and there is definitely a lot to see in SolidCAM 2019 as well. So without any further ado, we will make Amod Ankar the presenter, who is our expert and guru when it comes to 5-axis simultaneous. One note is that this webinar is being recorded and will be available for everyone to review as well later on. Okay, so Amod, I will make you the presenter, and you can unmute yourself and go ahead.
Thank you very much, Sydney. Hello, everyone, and welcome to this webinar on SolidCAM, what's new in 2019 for simultaneous 5-axis. I have differentiated, or I have made some segments, or precisely to say we have made 3 segments. One is a general improvement, what we have in SolidCAM, few of them. And then we're going to talk about 2 major aspects of the improvements in 2019. One of them happens to be a completely new machining strategy called as MultiAxis constant Stepover. And we have got a completely new support for circle end mills, or the barrel tools that we have today in the market. So we are going to see all of them, and plus some very nice case studies of multi-blade that we have made against some of the best in the market. I'll show you also that particular presentation. In this, we are going to have some presentation and also some work. So let's begin. It's what new. We introduced in 2019 in SP2 something called as a gradual front shift. This basically what it does is it basically shifts the contact point, which in default was only at the center. We make it move from the front to the back as it progresses over the cut. So it starts, the first contact point is in the front, and as it progresses over this cut, over the surface, and as it comes to the end, the contact point moves from front to the back gradually. Now this is a very interesting change we've made into our product. I'll show you the part also for this. So let's get into SolidCAM, and let me open a part. So let's front shift. Right, so we have this particular part here, and if I have to machine this surface, so if I run the Toolpath, if you see that in the tool axis control in the advanced, we earlier had only the auto, and at user defined point we only had the front shift and the side shift. Okay, we just had two values. Now we have introduced the to button. So in front shift we have got from, which is the default, and to, which is the new button. Okay, so let's look at how the toolpath now looks at the old method of working with the auto. And this is how it happens. You can see that we take the center point as our first contact point, and as it goes and progresses over the surface, okay, you can see that the contact point still remains at the center itself. Okay, so this was the old function. With a new one, what we have done is the function called as front shift. So here I have used at the user defined point, and my front shift starts at 50 millimeters. That's the tip of the tool, the front tip, and it goes all the way to -50, which is the back side of the tool or the back end of the tool. Okay, so let's run the simulation, and you can see that where it gets into contact with the first point, it's the front of the tool, and as it progresses ahead, the contact point changes. It's gradually changing the contact point. So when it comes to when the angle is 0, my contact point will always be, or rather it'll be at the center. And as it progresses towards the end, you'll see that the contact point is now changing and it is moving to the back side. So when it leaves the job, the final contact point will be the back side of the tool. Where would this application, or rather, where would you apply this particular function? I would say that if you're trying to use disc type of cutters and you would like the tool to have a uniform wear on the on itself, that's where you could apply this one of the applications. The second possibility is, let's assume that you are doing a polishing, okay, a 5-axis polishing of the surface, and you would like the entire polishing tool to take to rub on the surface. That's where you can apply even this particular method, right? So that's about the front shift. Like I said, you can use this feature for shifting the tool contact point as it moves along the contour of the surface. And this feature can be used in the machining process, where in the beginning, the machining process, the tool sits in the front, and at the end, it runs on the heel, basically in the polishing kind of environment that you would like. You can use this. We also have introduced different feed rates when it's taking a step over, or links now get different feed rate. They don't run with the same feed rate as the cutting feed rate, but now you can have a completely different feed rate. For example, in the same file, if I go over here and edit this, if I go into the link, and now you can see that I can apply a different feed rate when the links are happening between slices, and also when you're getting gaps, you can the feed rate. So if I have a feed rate here of 1000, I know that when it takes a step over, so let's simulate it again. I know that when it takes a step over, it drops down the feed rate to 500. And when it finishes the step over, when it comes back again into the cutting zone, the feed rate comes back again to 1000. So this is the place where the feed rate drops to 500. So this is the place where you can change the feed rate. You can either increase it or decrease it. Directly, the values can be input to whatever the feed rate you want. So another new feature that we introduced in 2019 is that now you can apply different feed rate at stepovers or links. Another important thing we made a change was to have a new kind of a parameter to smoothen out toolpath. Earlier, what used to happen was that the corner rounding used to happen only on the last pass. So if your last pass was something like this, you could round out only your last pass and not anything after that. But with a new smoothing option, I can now round out or do a smoothing on every pass, subsequent pass, apart from the one that is close to the wall. Okay, so in this case, there are two parameters. One is the smoothing. Basically, this would be called as a smoothing distance. And then you have got the detection angle. Now, what is smoothing distance? For example, if you look, if I have a toolpath that's something like this, and when it smoothens out, it puts an arc this way. Now, this distance is what we call as a smoothing distance, because that distance will now decide the arc size. Okay, so this is my smoothing distance, and this. So using these two parameters, we do the smoothing, and it can do the smoothing of the entire slices. Let's look at a part. Okay, let's come out of this. Let's open. Okay. All right. So what we have here, we have one toolpath. We can see that if I use a corner rounding, only the final pass is being rounded out. But if I use the smoothing, I go to tool parameters, and if I say apply a smoothing distance of 5 and a detection angle of 20 degrees, you can see what is the difference in the toolpath. So you can see that I get a nice corner rounding on the complete toolpath all the way to the final pass. So I can now have very nice changeover of directions even in 5-axis. Right, those were the three, you can say, small improvements that we brought into 2019. But the big improvements have been, like I said, two major ones. One is introduction of a new strategy and support of barrel tools, and of course the machining strategies using these tools. Right, so presentation. So we have now come up with a new machining strategy called as multi-axis constant stepover. What is multi-axis constant stepover? With a multi-axis constant stepover toolpath engine, SolidCAM now provides a next generation, or it's an evolution in the field of pattern generation. It's basically a pattern generator. That means it generates a pattern of toolpath which has got a constant stepover which you can easily measure, and this stepover is kept constant even on steep and shallow walls as it machines different surfaces, or it also can machine a mesh. So SolidCAM uses a global distance field without a fixed direction. That means generally when you ask for a stepover is always calculated with reference to a direction, the vector direction. But here we use a global distance, we use a stepover without a fixed direction as a reference, which enables us to be fully flexible in terms of calculating various types of patterns while maintaining a constant distance between, or consistent distance between, the cuts. The best part, it works on mesh. That means you could provide a mesh data to the engine for calculation, or you could provide a group of surfaces for it to calculate the constant toolpath. Very important, as you look at those figures here, you can see that right from the fillet, which is here, this fillet, up to this fillet, we have got consistent single toolpath. Once there is an engagement into the material, The final pass is finished only when it comes out of the final surface. So it continuously is wrapping around with a constant step over. Okay, it doesn't matter whether it's machining on this surface, or it doesn't matter if it's machining on this surface, or it doesn't matter if it's machining on the fillet below. The step over is constant and consistent throughout the group of surfaces. It works very nicely even in undercut situation. So in an undercut situation, like an example that I've displayed here, uh, SolidCAM's multi-axis constant step over engine, it generates same consistency of slices when it's making the pattern. That means it starts with a step over, let's say at this point here, and it consistently goes on creating step overs on the entire surface, maintaining a constant distance between the two cuts as it enters into this part. So even on this fillet, you will have constant tool path, and once it goes inside also there will be a constant tool path, and once it comes to the center it will retract up. So you'll see that there is one entry and one exit. All this tool path is now having constant step over between the passes, consistent. Most important, in another given situation where you have got an undercut machining, multi-axis constant step over coupled with automatic tilting gives consistent and reliable results. Automatic tilting in SolidCAM has actually been the most reliable way of avoiding gouges or collisions with neighboring surfaces, and the tilting uses a completely new engine now. It's extremely reliable and gives you very good results when you're using automatic tilting. So when we couple the multi-axis constant step over toolpath with auto tilting, you get one of the best results with the toolpath without having any kind of collisions either with the tool body or with the holder. I'm going to show you a few examples where it comes so tantalizingly close to the part, but it keeps maintaining the clearance distance that has been specified by the user. Now, the best part of multi-axis constant step over is that we have now created a subset which generates only 3-axis portion of the entire strategy. So we have removed the 3-axis from the multi-axis, and we have provided a new subset which is called as SolidCAM's multi-axis constant step over, but in 3-axis. The best part is that it generates extremely good toolpath even on 3-axis parts. For example, you can see here I have provided two curves, inner curve and the outer curve, and the mesh for it to machine, and it consistently generates a toolpath with a constant step over right from start to the end without lifting. The same example, we took a much more tighter area center. I provided only one curve, and I asked this multi-axis constant step over engine to generate cuts parallel to that curve till it finds no more cuts possible. So this is how it generated the toolpath. Okay, and these toolpaths are already Gouge checked automatically inside the software, so you did not have to provide anything special to it unless you need to provide it. This is what for 3-axis. So the best part is that it works either on group of surface, or you could provide a mesh straight away to it, and it will generate the toolpath on either the mesh or group of surfaces. We have got two patterns available inside multi-axis constant step over. One is parallel to multiple curves or morph between two curves. This also means that if you're using SolidCAM's generic 5-axis, you can move your toolpaths which we're using parallel to curve and morph between two curves into the new engine and get much better results, much better toolpath. Also the fact that you can now give a mesh to it makes it much more easier to calculate. So you can take all your toolpaths that we're using parallel to curve and morph between two curves and push them into the new engine for calculation. Okay, let's look at the part. So let's parts. So let me open the first part. This was the part. So what I have here, if you look at the definition, the first definition is I have got the tilt lines. So I've defined about 8 tilt lines, and the tool will use these tilt lines to maintain the tilt right from the start to the end. I have got a curve to which the toolpath is going to be parallel. So I have defined this curve, and I've said that now generate a toolpath that's going to be parallel to these group of faces. So here are a group of faces, and it's going to be parallel to the curve and machine this entire group of surface. So what is the result I get? So if I look at the result I get now, it's consistently maintaining a constant step over throughout, whether it's machining the fillet, whether it's machining the face here, again a fillet or a flat surface. It's exactly not flat, it has got some small curvature to it. So if I run the simulation of HostCAD, this is how my simulation looks like. You can see that it's applying the tilt and also machining consistently on the surface, maintaining a constant step over that I have asked it to. Constant step over means that you now are going to get consistently very good surface quality. So you can generate this toolpath either from outside to inside to out, or the standard method depending on the geometry that's being provided to the software for calculation. Okay, this was one method of showing you the multi-axis constant step over. The other method is out here where we have two curves. One is the inner curve here, this one, and one is the outer curve. That's this one. And top of that, I have got a boundary that I've defined. And of course, the tilt lines. So what do I get with my multi-axis constant step over? And in this case, I have not used faces, but I've said directly machine this entire mesh that it's being provided. So if I look at the toolpath, this is how the toolpath comes up. Constant step over right from the start till the end. So you can see that it just keeps on machining, and we have used the spiral method, so there's absolutely no step over. It's great. It's gradually machining the entire mesh till the final pass is generated. So a very interesting machining strategy. You can apply it. You can apply to your new paths. If you're having issues with parallel to curve, or if you want a better tool path in parallel to curve, morph between two curves, you can use new multi-axis constant step over toolpath engine and generate extremely good toolpaths. Okay, let's look at another file, a different kind of a geometry. And this is what I showed in the presentation. So this is a geometry I have. So if I take this geometry, you'll see that this is how it looks like. Okay, so I've got almost like a torus inside with fillets on either side. So what I have simply done here is I've selected the surfaces. I've picked up this fillet and the surface. And what we have inside the multi-axis constant step over is that the morphing need not be provided by the user. You can ask the software to automatically generate the machining curves. So the software now finds out which are the open areas and where it can generate good quality curves. It picks up those curves and generates the toolpath. So how is my toolpath going to look like? My toolpath looks something like this. So it starts and ends, very nice, consistent step over. And the best part is that we have used in the Gouge check, we have used the automatic tilting mechanism. Okay, so if you look at the simulation now, we've used a lollipop tool in this case. So let's increase the speed. And as it goes inside, you can see that it's very precise to the fact that it will not touch any of the areas. It will maintain whatever is the clearance value that we have specified here. It will maintain the clearance all the way down into the part. So if you run that, allow it, I'll allow the holder to get in, and then I can show you the how close it gets to the part. Okay. Can get to the part. So the holder is already inside, and it's maintaining that particular clearance that I've asked it to maintain, the 2 millimeter clearance. It's maintaining the millimeter clearance all the way down to make sure that it doesn't collide against the geometry, and thereby machining it with a constant step over. Okay, so a very interesting machining strategy. Let's move on to another part. This was a much easier one, so let's open another part. Like I have this part here, okay, which has got almost a nice spear inside. There's a torus geometry outside, a fillet, and again another geometry. So I have got a complete geometry, and if I have to machine this complete geometry today, I'll have to split this into several tool paths of, first of all, to machine this, and then to machine the fillet, then to machine this fillet, and then finally machine the inside. But still, I'll not be sure about the results. Now, with the new function, I can immediately generate a single tool path right from the start till the end. I've simply asked it. So if you can look at the parameters defined, I have asked SolidCAM to generate cuts parallel to this curve. So it's going to go parallel to the curve with this particular curve as my boundary. It's big part, that's why it's the boundary. And I've selected all these faces. Okay, just selected the faces, and this is the toolpath I generate. And if I run the simulation, you can see that the tilting is happening automatically, and as it goes up, you can see that it's maintaining that nice gap between the arbor and the part. It's pretty close. That's because we have used only 0.5 millimeter here. And as it goes up, you can see that it still maintains that distance. Okay, still maintains the distance between the arbor and the part. And here again, we have used what we call as the auto tilting. So here it's almost 3-axis as it comes up. Starts going inside, again starts generating 5-axis tool. Very nice, neat toolpath, extremely clean toolpath. The best part is being a single toolpath means that you will not have any mismatches of surfaces. Consistently, you can get a very good surface quality. Now, imagine if this was not machined with a lollipop cutter, and if it was to be machined by a ball nose cutter, how it would be. So here in the second toolpath, I have used ball nose tool, the 16 diameter ball nose. So if I just run the simulation, this is how the simulation would look like. Very short tool, and here also we can see that the 2 millimeter clearance is maintained between the holder and the part. And as it comes pretty close, you see that it's maintaining that. Now this is what automatic tilting does. Okay, you can see very nicely the toolpath is being generated. The step over is constant, even in the fillets or as it goes on to the spherical portion, it's consistently keeping the same step over. And as it goes inside again the same step over. Even on the fillet, it's maintaining the same step over. Okay, so very nice Toolpath engine. And for those people who would like, you can get in touch with your resellers or your SolidCAM office and ask for the upgrade to this version where you can run your toolpaths using this new engine. Right, that was about the multi-axis constant step over engine. Let's look at another major enhancement that we did in 2019, and this was the a long pending request from majority of our customers and even our own staff about the support for circle end mills or barrel tools. Starting 2019, we now support 4 different forms of circle end mills: the barrel shape, oval form, taper form, and lens shape. So we are supporting 4 different shapes of barrel tools. The reason being, more and more tool manufacturers are now introducing this new product line with barrel profile. Tool manufacturers now claim approximately 90% reduction in machining time when using circle end mills. SolidCAM, we introduced it in 2019, and we support 4 different shapes of circle end mills. Why do you need circle end mills, first of all? One of the reasons why we need a circle end mill is that, assume that we have this situation. We have a wall, and then we have got a floor here. Let's assume that the wall is about 100 millimeter long. It means that if this wall has to be machined, I will have to use an end mill of at least 105 millimeter out of holder, and then use the side of the tool. We'll have to use the side of the tool to cut the part like swarfing. But at 100 millimeter overhang, I'm not sure if we are going to get a very good surface quality here. So in order to avoid that, sometimes we resort to ball nose tools. But the problem with ball nose tool is that it has to use, if I tilt it, still it'll be on the ball profile. Okay, let's assume that this was a 16 diameter ball nose tool. Okay, this was a 16 diameter ball nose. And to generate a scallop or a cusp height of, let's say, even 0.005, it would need a step down of about 0.5 millimeter. Now, assume with the new oval form tool, instead of R8 on the side, I am going to get about R75. Now, to get the same or even lower cusp height, I can straight away go to 3 times the step over. That means I straight away reduce the time 1/3 of what I would generate using a ball nose tool. So circle end mills are actually making a big revolution in machining, where they can generate a larger step over while maintaining the same cusp height when you compare it with the ball nose tool. Now, there are some pluses and minuses when you're using the circle end mill. So let's look at both of these. Now, this was one of the reasons why circle end mills came into picture. One of the other reasons was that when you're machining deep surfaces or long surfaces, you could potentially have a tool deflection. So when you have a tool deflection in this way here, there is every possibility of these cusps or the inaccuracies creeping up when you're machining the surface, especially when they are pretty deep. Okay. Now, barrel mills are also prone to these vibrations, okay, these inaccuracies. But because of their shape here, even if it gets a vibration or it gets an inaccuracy in this direction, because of the radius in contact, the same radius or the same portion of the tool still is in contact with the surface. So the inaccuracies in that creep in because of dynamic imbalances that happen during cutting is very, very less when using barrel mills. Okay, so it can generate a low cusp height. It can balance machine inaccuracies like what I showed here, smooth transition between cuts, and lower dynamic disturbances because we use shorter tools, because we always go in contact with the side of the tool, and thereby we can really use short tools to machine deep surfaces. So one of the another advantage using barrel tools. The next advantage, like I mentioned in the very first slide, was that when you're machining deep surfaces, you tend to get these restrictions. You tend to get the height restriction. The tool height restriction comes into play. Now, because the tool height restriction comes into play, with barrel tool, what you can simply straight away do is you can tilt the tool and yet generate a very small cusp by generating a higher depth of cut or higher step over. The another advantage with the barrel tools, especially the overform tools, is that it has got a dual radius, a small radius in the front and a large radius on the flank. You can actually use the small radius to machine the leftover materials in the corner. So the tool remains the same. You don't get any mismatches. So this is another great advantage when you're using barrel mills or circle end mills. Now, we saw where we could use circle end mills, but there are several places where you actually cannot use them. One of the places where you cannot use them is surfaces with convex which are orthogonal to the feed direction. For example, like a spear, where it's better always to use a flat end mill, and Stepover is anyway limited to the part curvature, so it's not possible for or rather the barrel mills don't give us a great significant advantage over flattened mills when machining such surfaces and should be avoided. Another important area where you cannot use barrel mills or barrel shaped tools is that when you have surfaces where it's concave and the radius is smaller than the barrel radius, you cannot use. It doesn't make any sense. There it makes more sense to use a ball nose tool to machine the area, because the tool won't anyway reach in with the barrel section. When you're having a 3-axis machine, it doesn't make any sense to use barrel tools, because you cannot get the flank of the tool in contact with the part. You'll always be using the front or the tip of the tool, which is anyway the weakest point in a barrel mill because of the small radius. In this case, it's better to use a regular ball nose tool, and that will give you a much better result. It is more robust when it comes for machining in 3-axis. So these are the areas where generally you cannot use circle end mills. The other big challenge is that when you have surfaces with varying curvature, for example, as long as you have got a simple straight or simple surfaces, it's easier for barrel tools to calculate the step over to maintain the cusp. However, the moment you get a situation where you have got a different curvature in this region, then the region here, then we get into a situation where you need to generate a much smaller side step than what you're going to use in this region here. So again, we are not yet geared up. Softwares are not geared up to handle this situation. So we are still working. There's still research going on. This is again one of the challenges with barrel tools, which has not been addressed till now. Also, the other challenge, like what I explained to you, that barrel tool has got the tip, which becomes its weak point. So you now need to identify, or the softwares now need to identify, which areas need to be machined first and which areas that need to be machined next. For example, when you're in this situation, it's always better to machine the bottom along with the fillet first clear it, and then machine the flank. Because if you directly go to machine the part, or if the material is present on the flank and as well as the floor, the time the tool comes down on the flank and starts getting into the fillet, you will get a bigger force acting on the tool, because the material is now encompassing over the entire small area of the tool, which is in any way the weakest part of the tool because of the small radius, and thereby the wear increases. So softwares now are trying to become smarter by identifying areas which need to be machined first and the areas that need to be machined second. So in our case, this would be machined first and this would be machined second. Fillet first or bottom first, and then the flank. With 2019, we also now have introduced a new tilting method, because it was not enough just to have tilting based on an angle. We now have tilting based on the contact point. So there are two options available. One is by height. That means you specify what is the height of the contact point with reference to the tip in the machining direction. Okay, so if this is the contact point, let's say here, then SolidCAM will generate the it will generate the angle automatically with reference to the tool axis. You don't need to specify any alpha angle. Okay, now if let's say the wall has got a fillet at the bottom, it has got a fillet, or rather a floor at the bottom. In that case, if I continuously keep using the same point, a point will come when the machining will just stop here. It will not go anything because the contact point is already here and the tip is already touching the bottom floor surface. So the tool path will terminate there. To avoid this situation, we have got another method of working, and that is called as the line parameter. That means we distribute the contact points throughout this barrel section. We start with end of the barrel section as 0 in terms of percentage, and here the start will be given as or rather this the end will be 100%. So we can now say distribute the contact point from, let's say, 80% to 10%. So it will keep putting the contact points on the line or on the barrel profile and determine for each of these contact points what is going to be the tilt angle. Okay, the tilt angle will now be determined by the contact point and not just by the angle. The angle, of course, is already available with us, but we also have got this new functionality, and in both the cases, what we call here, this is a static case and this is a dynamic case, or static point and a dynamic point. So both the modes are available now with barrel tools. Okay, so you have got again here the static mode where you have got a single contact point. So this contact point will remain always same. So even when the tool comes here, the contact point will be the same. It will stop the tool path. So your tool path will be only up to this area. Anything beyond this, now you need to change. If you move to the dynamic mode, it will start with this contact point. However, it will end with the contact point at the bottom. Thereby, it will be able to machine the entire surface right up to the fillet. Both these modes are now available to the user. In the tilting or in the Gouge check, you have now got automatic tilting, and we have got a special smoothing feature for automatic tilting only for barrel tools. Okay, so the automatic tilting is now available for barrel shape, oval form, and lens shape tools. The difference between automatic tilting for spherical tools and barrel shape is that the dynamic side tilt will result in an additional retract because it is off center. It's not like our spherical tools. If I show you an example here, if I just make a small drawing, if you look at our spherical tools, the center is always here. So even if it rolls on this periphery, the center remains at the same place. However, with a barrel tool, the center of this particular arc will be probably somewhere be here. Even if this is a tool, the center will be here. So when it does the automatic tilting, there is always a small chance retract along the center axis. A small retract happens along the center axis, and that's how it works. Because the barrel profile center is always off axis. It's never on the axis. Okay, so let's look at a nice example. Let's open circle and mill. So I have my part here. I've deliberately made it like this, so it's pretty deep. So if I measure, and this is approximately about 125 millimeter, and this is not a straight surface, but it has got a very high curvature. It has got a curvature of 900 millimeters, so it's not a straight surface. So obviously we cannot use an end mill here. We have to use ball nose, or I have to use a barrel tool. So what I have done here is I've created a toolpath using morph between two curves, where I have my geometry, and I have two curves, the upper curve and lower curve. The tool I've used here is an EMUG oval form tool with diameter 16. The bottom radius is 3 millimeters, and the major profile radius is 75 millimeter, and out of holder is only 55. Okay, it's a small tool. Using a tool which is outside by 55, and we are machining a deep area which is 125 millimeter deep. In the tool axis control, you can see that I have using the new function called as the contact point, and here I have said that distribute the contact point from 50% all the way up to 10%. So it's going to be, so if I look at the tool, so if I look at the tool here and I zoom this and I take up the picture, so what I have here is that this is 0, this is 100. So my first contact point on the tool is going to be here at 50%. So this is the point where it will generate the contact point, and it will start distributing this contact point till it reaches 10%. So it will start putting depth cuts all on this, and the tilt axis or the tilt angle will be determined by where is the contact point on the tool between 50% and 10%. So this is what we are going to see here. And I have also used in the tool axis, in the Gouge check, I have used a couple of them. I first trimmed the tool path against my check surface, that's the sides. I don't want it to collide, so I've trimmed the tool path, and then I have used the automatic tilting for barrel tools only to have a collision check only with the holder, because I'm sure that the cutting part and the arbor is not going to collide. We are going to have only collisions with the holder. So how do I get the tool path? Tool path is pretty straightforward. If I show you the tool path, how it looks like, this is how it is generated. I've used what we call as the automatic arc. So it's just retracting on the same level. And now if I show you on the side view how the contact happens, I said that my first contact is at 50%. So let's run the simulation. So you can see that my first contact point, like my drawing, is at 50%. So it starts with the first point at 50%. And let's run the toolpath. You can see that as the contact point changes and starts coming down to that 10% mark, the tilt angle keeps on changing. Okay, it keeps on changing till it finds the final tilt line. So let's run it again. close this. Oops, I think there is a problem. Went into a loop. Let's start it again. Cancel. Okay. I see that there are some questions. I'm going to take those questions at the end. I'll just finish with my presentation and the parts. Let's go back again here. Okay. Let's go to the side view again. And let's run the simulation. Side. Okay. Again, it's like I said, it starts at 50%. As it goes down, it keeps shifting the contact point all the way down till it reaches a point when the final 10% is taking the contact. And this is when it will stop and it will retract up. Okay, that's the final toolpath. Now, this is done by the software automatically, so you just need to define your starting contact point and your ending contact point, and you can get a very nice toolpath. Now, what happens to the fillets? You can use the same tool and generate toolpaths using morph between two curves. And what I have done here is I've simply defined two curves, and it generates a toolpath. Let's reduce the speed. And this is how it does. And here again, we have used the auto tilt mechanism. Here you can see that we're using the tip of the tool. So we are using all the portions of the tool to machine also the fillets. Okay, and in the automatic tilting, the software takes care of changing or avoiding the collisions with the holder and the part around it. Okay, so in the same way, I have machined the bottom fillet. What I've done is I've defined one point out here, and I've used this point as a point for my tilting. Again, with the same tool, you can see that again I'm using with the tilt, with the tip of the tool, not tilt, with the tip of the tool. And we finish the fillet. Now for the face down here, okay, this is not flat, it has got a small curvature to it. So here I'm using another kind of a tool from the lens shape of from the barrel tool. It's called as a lens shape, and in the lens shape it has got a very nice curvature at the bottom. So it's like a flattened mill. Okay, it's like a flattened mill. So if I show you the tool, let's increase the size. Okay, if I show you that, it has got a very nice curvature at the bottom. So it has got a big radius here of and then there is R1.25 also on the side, and it's a 12 diameter. So what I'm going to do here is I'm using somewhere this point on the large profile and generate the toolpath. So what I've done here is, again, I've used morph between two curves, and I've defined this surface for machining. And in the gouge check, again, I've got tilt tool with the check surface. So it's going to tilt the tool automatically to avoid gouging against any of these surfaces that you see here. No other gouge check has been used. Again, oh, no. If I again run the simulation, this is how my simulation would look like. Okay, it's just using the front of the tool. I've set the tool to be at 50% of the barrel profile. So the tilt again is calculated automatically by the software, and also the gouge checking is done automatically by the software. So that's how it generates the machining. So we can now use any of the barrel shape tools, either it's a barrel shape, oval form, taper form, or lens shape. You can use any one of them. By the way, we also support a double barrel. It's called as a double barrel, where it has got a large radius on the side of the flank and also a large radius. It's like a combination of a barrel tool and a lens shape. So we also support that, but we can integrate, or we can implement it only if there is a requirement from the customers, a very serious requirement saying that this particular tool is being used very widely, so please implement this tool. We can immediately implement the support for that tool also. Right, so as far as the features are concerned, we're done with the features. I just want to end this up with a very nice part that we did against some of the best competition available to us today in the market, which are specializing only in machining large multi-blade parts. So this was the part that was given to us, and this was the final result on the machine. This was done using DMU65 monoblock with Hydradyne ITNC 530. This was the first roughing, the stage of roughing. Again, roughing, we used two different tools from Moog here to do the top roughing with a 10mm depth of cut, and then we reduce the depth of cut to 5mm using a longer tool. The length of this blade here is about 85mm, so it's pretty long, and the worst part is it's pretty thin. It's like 1.8mm thin all the way from top to bottom. Okay, so we did this excellent machining with SolidCAM's multi-blade capabilities, and we were at par with our competition, the best players in the market for machining such parts. Okay, so this part was done completely using the SolidCAM's multi-blade machining technology, and we used the tools from Moog. We used two different tools. One was a 12 diameter taper ball nose with 4 degrees taper, and bulk of the roughing was done by 10 diameter 6 degree taper tool. So we use this excellent tools to machine, and the result also was very nice. We were at par with competition. So as far as 5-axis goes, we are at par with most of the top 5-axis machining solutions today in the market. We can machine any part, we can support any kind of tool, and we can support any kind of machine, including the post-processor strategies and the machine simulation. So we can offer a complete solution for any kind of 5-axis part, whether it is impellers, blisks, or port machining, or parts machining with 5-axis, medical parts, die mold, you name it, and we have a solution inside SolidCAM. Very powerful solutions inside SolidCAM for 5-axis. Thank you very much for patiently listening to my webinar. I have some questions, if I'm not wrong.
Well, actually, I have only just one question, really.
Okay.
And you can see it right at the very beginning. What is the best and safest way to mirror or transform 5-axis operation?
If you have, let's open a part. Because what we have in SolidCAM is that you can now straight away pick all your operations, right click on them, and you can go into the mirror functionality. I've just disabled it for this particular setup, but you can just directly mirror, either you can mirror a single toolpath, or you could mirror the entire operations itself. Okay, I have just disabled the major mirror here for this particular webinar, because it's a development version that I'm showing you. But you could directly pick the entire project as it is and mirror it straight away. We support mirror on individual toolpaths, and we also support mirror on group of toolpaths, or straight away the entire project itself. And you can be rest assured of the results, because we have developed this very powerful algorithm inside SolidCAM. It's a powerful engine for mirror, where it does an excellent job. The best part is that we do not exactly mirror the toolpath as it is, but we have made the engine is so powerful that it actually mirrors the geometries that are used in the toolpath, and then it calculates the toolpath. So your climb milling on your part stays pure climb on your mirror toolpath. The direction of machining doesn't change. The direction remains the same. And that's the best part of this mirror.
Okay, Ahmad, thank you again. We've come a long way since we've started 5-axis, and we truly say over here that we are definitely extremely powerful with our new tools in 5-axis. Again, thanks again for the webinar. This webinar has been recorded, and it will be available to everyone later on at a later date on our website, www.solidcam.com, underneath the webinar tab as shown over here. Okay, again, thank you very much and take care and have a great weekend.
Thank you.